Hello and welcome to Pep Talk with me, Mr. Pepperell. Today I'd like to introduce you to the fuel of the future. By the end of this episode you should be able to tell me, what is nuclear fusion, how can nuclei be made to fuse together, and where does the sun's energy come from?
So previously we've looked at how we can release all the energy locked up in the nuclei of atoms by breaking apart large nuclei during nuclear fission. Okay, but now we're going to look at another way to tap into this massive energy store, and today we're going to talk about the process of nuclear fusion. Now this also releases a lot of energy, and this time by joining or fusing together smaller nuclei, and this is exactly what happens in stars, and they're pretty energetic. So let's find out what actually happens. So nuclear fusion is the joining together of two small nuclei to form a single, larger nucleus. And in fact, energy is actually only released in this process when you fuse together smaller nuclei. And when I say smaller, what I actually mean is anything with a mass number lower than 55, and 55 we know is iron. So if you start to try and fuse any element bigger than iron together, okay, you actually need to put energy in to make a bigger nuclei. So iron is our sort of barrier to getting energy out of nuclear fusion. Now, you're actually fully aware of nuclear fusion because it's actually what goes on in the sun, okay? Now, the sun, which is our local star, is made up of about 75% hydrogen and about 25% helium. And I think you can probably guess that it is very, very, very hot in the sun. In fact, you know, on average, the core of the sun is at about 15 million degrees centigrade. And at that temperature, something funny happens to these hydrogen and helium atoms inside of it. They get so hot, basically, they get so much energy that the electrons get stripped away from the nucleus, and you are left with what is called a plasma. You've just got an ionized gas there, the electrons have been stripped away, and you're just left with positive ions, which are the nucleus of the atoms. So you've just got all these bare nuclei whizzing about inside the sun. Now, as these nuclei move about, like the one we've got here, very occasionally they will collide into each other, and when they do, they join or they fuse together, and when this happens, energy is released. Okay, and that's why our sun is so very hot and shiny. Okay, so let's have a look at this process in a bit more detail and find out exactly what's going on here. So in this process we're mainly looking at protons and neutrons that we're familiar with. Now there are some other particles involved down here, okay? You don't need to worry about these at all, okay? If you want to, we can talk about those a bit more in the lesson, but don't worry about these for now, because all we're going to deal with is the protons and neutrons basically. Okay, so we've got up the top here, we've got two hydrogen nuclei, which are basically just protons, and what they are going to do is they are going to collide together. Okay, now when they collide together, what we can see is that one of them is converted into a neutron, and we can see, like I said here, that these couple of other particles are emitted, but we're not going to worry about those for now. Okay, now our new nucleus is still hydrogen, because remember, it's still only got one proton there, okay, so it's still a hydrogen nucleus, but it is now an isotope of hydrogen, which is called heavy hydrogen or deuterium. And somewhere else in the sun, this is also happening to two other protons, okay, so we can see that what we've got there is, through this little process, we've ended up with two heavy hydrogen or deuterium nuclei. Now, the next step is that another proton collides with each of our two heavy hydrogen nuclei, or our deuterium nuclei that we've got here. So these are other protons that are just whizzing about, and they're going to collide with our heavy hydrogen nuclei. Okay, and when they do that, what they do is they form another larger, again, nuclei. This time the nuclei has got two protons, one neutron, and we call this tritium. So this is our tritium, which is another name for helium-3. It's not hydrogen anymore because now it's got 2 protons. So now it's a helium nucleus, but it is an isotope of helium. Normal bog standard helium will have 2 protons and 2 neutrons. This has just got the 1 neutron here, so this is an isotope of helium. And of course, this whole process has happened over here as well with our neighbouring deuterium atom. So at this stage, we've now ended up with 2 helium-3 nuclei, or 2 tritium nuclei. So the final step is that our 2 helium-3 nuclei collide to again form an even bigger nucleus, okay? And this time, 2 of the protons that were involved in these 2 nuclei here, they fly off, okay, and they leave a new nucleus consisting of 2 protons and 2 neutrons. And this is the standard nucleus of a helium atom, but of course no electrons, so it's a helium ion here, okay? Now, these 2 protons can now whiz off around the sun again, and they can whiz back up here, and they can start the whole thing over again, okay? Also, what could have happened is, one of these deuterium atoms here could have collided with one of these tritium atoms here, and that could have fused together again to make helium, but this time only releasing a single extra proton. But basically what we've done, we've gone from small nuclei up here, fusing together via a number of steps to produce the nucleus that we know is helium. So where's all the energy coming from during all this process? Well, each time a fusion event occurs like this, an awful lot of energy is released by the process, okay? And there's an awful lot of these collisions taking place inside the sun, and an awful lot of energy being released every time. That all adds up to an awful lot of energy being released by nuclear fusion inside a star. So, back at the start of this episode, I showed you a glass of water, and I told you it was the fuel of the future. And that is because water, and in particular seawater, is already full of deuterium, okay? Well, I say full of it, about 1 in 6,500 atoms in the sea is actually deuterium of seawater anyway. Okay, so why aren't we just fusing all this deuterium together to meet all of our energy needs? Well, the answer is because it's not actually that easy to fuse nuclei together outside of a star. And in the next episode, we'll look at how we might actually do that.
So that's everything we need to know about the process of nuclear fusion. Any problems with that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.